Hey guys, in this video I'm going to run you through all the solutions for the Edexcel 2024 Pure Paper 1 for A-Level. Every question is going to be timestamped, so you can easily skip to a question or rewatch a question if you want to. Hope this helps. So here we are at the front of the paper, going to question 1. We've got a function g of x. It says given that x minus 3 is a factor of g of x, find the value of k. So that's factor theorem. If x minus 3 is a factor, we know that g of 3 must equal 0. So if we plug in 3, we'd have 3 lots of 3 cubed minus 20 lots of 3 squared plus k plus 17 times 3 plus k, and that must all equal 0. If we simplify that up, so let's add up all the constant terms. So 3 lots of 3 cubed minus 20 lots of 3 squared. We're going to get 17 lots of 3 from this guy. So plus 17 lots of 3. That comes out as minus 48. We'd have minus 48, and then grouping up the k terms, we're going to get 3k from this and this, and another k on the end, so that'd be plus 4k equals 0. So then k is going to have to be 48 divided by 4, sorry, if we rearrange. 48 over 4 gives us k equals 12. Okay, so now moving on to question 2. It says, finding ascending powers of x, the first 4 terms of the binomial expansion of 1 minus 9x to the half, giving each term in its simplest form. So first, let's just write out the formula for the first 4 terms. So for 1 plus x to the n, that's the formula we need, as it's not an integer power of for our expansion. That would be 1 plus nx plus n times n minus 1 over 2 factorial times x squared plus n times n minus 1 n minus 2 all over 3 factorial x cubed. And then we're just going to have to sub into that formula now. So 1 minus 9x to the half, we'll have 1, then plus a half times minus 9x, then plus a half times minus a half. 2 factorial just 2, so I'll just write 2. But it's times minus 9x all squared. And then the last term, I'll just put that down here. That would be a half times minus a half times minus 3 over 2 all over 3 factorial, which is just 6, but times minus 9x all to the power of 3. Then we can just simplify this up. So the first 2 terms are just pretty straightforward. So the 1's just the 1. Then a half times minus 9, that's minus 9 over 2x. Then from here, I'd probably just use the calculator. So in that x squared term, we're going to have a half times minus a half. And then we're going to get a minus 9 squared. And then that's all going to be over 2. That gives us minus 81 over 8x squared. And then if we just go and edit this now to include what we need for the x cubed term, so the denominator is going to be 6, and in the top, we're going to keep those guys, but we need to put in a minus 3 over 2, or a minus 1.5, let's say. And then this minus 9 now needs to be cubed. What does that give us? Minus 720, oh, that's an x squared, sorry. Minus 729 over 16x cubed. Then for part B, it says, give a reason why x equals minus 2/9 should not be used in the expansion to find an approximation for root 3. Well, first let's just quickly check it's a valid x value at all to put in the expansion. So when we use 1 plus x to the n, it tells you in the formula booklet that this is only valid for mod x being less than 1. So for us, we need mod of minus 9x to be less than 1. Or in other words, mod x needs to be less than 1/9, which means x needs to be between minus 1/9 and 1/9, which it's not. So therefore, x equals minus 2/9 is not a valid input. Moving on now to question 3. We've got a function f of x defined as x plus tan of a half x with a domain going from pi to 3 pi on 2. It says, given that the equation f of x has a single root alpha, show that alpha lies between 3.6 and 3.7. Well, if we assume it's continuous over that interval, and if we get a sign change over that interval, then there must be at least one root in that interval. So we'll assume it's continuous, which it is, and plug in the value. So if we do f of 3.6, let's make sure our calculator's in radians. Yes, it is. So we'd have 3.6 plus tan of 0.5 times 3.6. That gives us minus 0.686 ... Then if we do f of 3.7, just go back and change this to a 0.7. Oops, that's the point. Leave that there. 3.7. That gives us 0.211. So sign change. Therefore, at least one root in the interval of 3.6 to 3.7. Oops. 3.7. Assuming it's continuous. Then it says find f dash of x. So f dash of x for part B. The first bit in x just differentiates to 1. Then for the second bit, we need to worry about the chain rule because we don't just have an x here. We need to worry about that half x. So if we differentiate the inside first, a half x just becomes a half. And then the derivative of tan is sec squared. So it would be half of sec squared of a half x. And then it says using 3.7 as the first approximation for alpha, apply the Newton-Raphson method once to obtain a second approximation. So the Newton-Raphson formula is this. It's xn plus 1 is equal to xn minus f of xn over f dash of xn. So just writing that out properly for us, that's xn minus our function, which is going to be xn plus tan of a half xn all over 1 plus a half sec squared of a half xn. So testing that out in the calculator, or sorry, not testing it out, using our first approximation. So we're starting with an x naught of 3.7. So then x1, just plugging in 3.7 into our formula, we've got 3.7 minus fraction 3.7 plus tan of 0.5 times 3.7. Then we got 1 plus 0.5. And then to get a sec squared, what I'll do is we'll have a bracket, and then we'll just do 1 over cos of 0.5 times 3.7. Close that bracket, then close the big bracket, and then we need to square all that to make it a sec squared. Which gives us that, and what do we want to round to 3 decimal places? That would be 3.672. Moving on now to question 4. It says, given that y equals x squared, use differentiation from first principles to show that the derivative is 2x. So whenever we get this question, first thing we're going to do is write down the first principles formula. So that says f dash of x is the limit as h tends to 0 of f of x plus h minus f of x all over h. And the bit that students find difficult is normally working out what f of x plus h is. Well, first off, f of x is just x squared. So this function takes our input x and it just squares it. So if we want to look at f of x plus h, all that's changed is now our input is x plus h, but the function has not, so all it will do is take x plus h and all of it, so in brackets, and square it. Then we can simply plug that into the formula and see what happens. So we'd have the limit as h tends to 0 of x plus h all squared minus x squared all over h. Then we can't actually divide by h, so we need to expand the top. That's going to be a common thing that's going to happen. We'll have to do some algebra before we can evaluate our limit. So on the top, we would have x squared plus 2hx plus h squared minus x squared all over h. And then we can cancel off a lot here. This x squared goes with this. And then we've got everything has a factor of h that's left, so we can cancel off the h from here, 1 from here, and this guy here. So we're left with the limit as h tends to 0 of 2x plus h. Well, if h is 0 here, it's obviously just going to leave us with 2x, which completes the derivation. Carrying on to question 5. It says the function f is defined as 2x minus 3 over x squared plus 4. Can we show the derivative can be written in this form here? So to differentiate that, we're going to use the quotient rule. So first, let's just write that out. That would say f dash of x is, sorry, probably that bit better. So if we take a fraction u over v, which are 2 functions of x, and we want to differentiate it, it would become v times the derivative of u minus u times the derivative of v all over v squared. So for us, u is 2x minus 3. And v dash, sorry, not v dash, just v, is x squared plus 4. So then differentiating those to get the rest of our pieces for our formula, we'd have u is just 2, and u dash is 2, and v dash is 2x. Then plugging into the formula, that would give us f dash of x is v times u dash, so that's 2 lots of x squared plus 4, minus u times v dash, which is 2x times 2x minus 3, all over v squared, which is x squared plus 4 all squared. So we've already got the denominator of our answer. We need to tidy up the numerator to have it in that simplified quadratic form. So we're going to get a 2x squared from this expansion here, but we're going to get a minus 4x squared from here. So the first term is going to be minus 4x squared. Sorry, minus 2x squared. 2 minus 4 is minus 2. Then our x term, our only x term is going to come from this minus 2x multiplying the minus 3, and we've got to be careful because that's a double minus. So 2x times minus 3, that's minus 6x, but the double minus is going to make it a plus 6x. You go plus 6x. And then our constant terms is going to come from the 2 and the 4 here. That's a plus 8. Over x squared plus 4 all squared. Then it says, hence, using algebra, find the values of x for which f is decreasing. So if f is decreasing, that means our derivative is strictly negative for those values of x we're interested in. So let's just copy our derivative here. We'll paste this on the next page. Oops. Paste. We need to think, okay, well, when is this going to be less than 0? Well, first off, we can simplify the problem, because the denominator here is always positive because it's a squared quantity. So if the whole thing's going to be negative, but it's a positive in the denominator, the numerator needs to be negative. So we can simplify this just to minus 2x squared plus 6x plus 8 needing to be negative, which is just a standard quadratic to solve like quadratic inequality. So I would always just plot the graph here, but I think I'll make it even easier and simplify, so we can divide everything by 2. So let's do that. So that would be minus x squared plus 3x plus 4. And then I don't really like looking at minus quadratics. I prefer to deal with a positive, whatever. It's not a big deal, but I prefer to do that. So we could bring it all over the side, or the same thing is if we just multiply both sides by minus 1, but then we have to flip the sign if we multiply inequality by a negative number. So if we multiply by minus 1, or however you want to think about it, we'd have x squared minus 3x minus 4. But now we're interested in where that is greater than 0. And then that quadratic, we can actually factorize fairly simply, can't we? That's just x minus 4 times x plus 1. And then I'll always draw a little picture just to make sure I don't make a silly mistake. So this quadratic is going to have a root at 4 and minus 1. And then we're interested where it's greater than 0. So we're interested in this section of the graph, or all the x values less than minus 1, and all this section where all the x values are greater than 4. And does it ask it for an inset notation? No, it doesn't. It just says find the values, so I'm not going to bother with the set notation. So our answer then would be x is less than minus 1, or x is greater than 4. Moving on to question 6, we've got this modulus curve, we've got the equation for it, and first it wants us to find the coordinates of P. So P is the bottom of the V. That's going to happen when the modulus section here is equal to 0. So for part A then, the x coordinate is going to be 2. And then to find the y coordinate, we can just plug that in. So y would equal 3 times the modulus of 2 minus 2, which is 0, obviously, plus 5. So y is 5. So our point is just 2, 5. Then moving on. Actually, let's just label that for reference as well. That's 2, 5. So the next one is like solve the equation 16 minus 4x equals that same curve. So it's where those two lines intersect. I always like to try and get a bit of a picture for this. So it's going to have a steeper gradient because it's a minus 4 rather than just a 3. But it's also negative, and it's going to cut at 16. So It's a little bit. Let's think where would this point be first. That would be at be 6 plus 5, so that'd be 11. So it's going to cut above that at 16. And then it's going to be steeper than this line here. So it's going to come in like this. So we have to be a bit careful because it could potentially be if it was parallel, it would intersect like this, but it could potentially still intersect the right side of the V. So what we'll do is I'm as a slight guess, I think it will be the left side of the V, but we'll have to make sure that x coordinate is smaller than 2 for it to confirm it's the right solution that we found, because it would intersect with this line potentially. So let's do that. So this the left side of the V, we think about splitting this equation up. We could think of it as being it would be 3x and then minus 6 plus 5, 3x minus 1 for when x is greater than 2. And then if we go to the other side, which we're going to actually use, it's going to be minus 3x, but then plus 6 plus 5, so plus 11, when x is less than or equal to 2. So that's the side we're going to actually solve with. So for part B then, to find the intersection point, it's going to be 16 minus 4x equals minus 3x plus 11. So that's a simple linear equation to solve. So solving that, we would get, bringing the 4x over, we just have x, and then the 11 to the other side, that would be x equals 5. So actually, that's wrong, isn't it? That would mean it would be intersecting with the line somewhere over here. So that's not going to be right. So we need to actually solve with the other side. So that's not the right solution. We need the other solution. That would be 3x minus 1. Sorry, I flipped it around, but the same process. 3x minus 1 equals 16 minus 4x. So using that solution, and this time it's going to need to be bigger than 2 if it's going to intersect with the right-hand side of our equation. So solving that, we'd have 7x equals 17, or x equals 17 over 7. And I will just check quickly that that's actually bigger than 2. Yeah, it is bigger than 2, because 2 lots of 7 is 14. But let's just confirm in the calculator. Yeah, 2.42. So that's our solution. So just make it clear that that's the solution we want. Okay, then it says a line L, which is y equals kx plus 4. That's the gradient's a variable. Where k is a constant. Given that the line intersects this at 2 distinct points, find the range of values of k. So this is another one where visualizing it is going to help. So if I just get rid of this a second here. So from before, we knew that this point here was, what was it? It was 6 plus 5, so that's 11. So kx plus 4 is going to be somewhere further down here. And then the gradient's variable. So we have to think about like the slope of our graph changing. So let's think about first like the critical points where it would only intersect once. So one way it would only intersect once would be like this. So that's specifically where it goes through the point P, the 2, 5 point. And then the other way it could only intersect once is if it was running parallel to the right side of P like this. So this would be when the gradient is equal to 3. That value k is easy to find. So it's good, like the k is going to have to be smaller than 3, and then this is going to be the lower bound of k. So we need to find that, but we can find that because it must go through the point P in that case. So for part C, if we take our line, which was y equals kx plus 4, and we force it to go through the point 2, 5, that's going to leave us with 5 equals 2k plus 4. So then k would be a half. Yeah, a half. So that means k is going to be strictly greater than a half, because it needs to be a little bit steeper than k equals a half to intersect twice. But it can't go past k equals 3, because then it would run parallel and not intersect this section at all. So k must be strictly greater than a half and strictly less than 3. Moving on to question 7. It says figure 2 shows a cylindrical tank of height of 1.5 meters. That's marked on the diagram. Initially, the tank is full of water. So that's going to be, I'm just going to star that. That's important information. It could be about the height or the volume of water. It's definitely the height, isn't it? That means h is 1.5, actually. And actually, just looking quickly ahead, it's a differential equation in h, so we definitely want to think about h. The water starts to leak from a small hole at point L. While the tank is leaking, the depth h meters of the water in the tank is modeled by the differential equation, blah, blah, blah. Where t hours is the time after the leak starts. Using the model, show that h is this exponential function. So that's just the solution to the differential equation. So for part A, we just need to solve our differential equation. So the first thing is we solve all our differential equations the same in A-level maths. So we're going to have to isolate the function of t and multiply it by the dt, and anything with h, but there is no h, it would go with the dh if there were. So that would leave us with dh equals minus 0.12 t e to the minus 0. Oops, sorry, that t shouldn't be that. Just minus 0.12 e to the minus 0.2 t dt, and then we integrate both sides. For the integral of dh, you can think of that just the integral of 1. So that would leave us with the h. Then on this right-hand side, we would have minus 0.12 e to the minus 0.2 t, but if we were to differentiate that, minus 0.2 would come down, which we don't want, so we need to divide by minus 0.2. And then we'd have an integrating constant plus c. Let's just copy this line of working to the next page. So simplifying that down, 0.12 over 0.2, because those signs are going to cancel. That's 3/5 or 0.6. We'll write it as 0.6. Those are the minus signs will cancel. Sorry, that's what I meant to say. 0.6 e to the minus 0.2 t plus c. And then to find the plus c, we're always going to need some conditions. So that's where that note I made before is going to come useful. It says, well, the tank is full of water. It says initially, so that's when t equals 0 as well. So we have that condition to use, h equals 1.5 when t equals 0. So plugging that in, we would have 1.5 equals 0.6 e to the 0 plus c. E to the 0 is just 1, so we have 1.5 equals 0.6 plus c. So c must be then just 0.9. So our full solution is 0.6 e to the minus 0.2t plus 0.9. So that's part A dealt with. Then it says, find the time taken for the depth of the water to decrease to 1.2 meters, giving your answer in hours and minutes. So that's, make sure we always check the units when we do this. So t is in hours, so we're going to have to mess around a little bit to get hours and minutes in a second. But if we're interested in when it's the height is 1.2, all we need to do is set h to 1.2. For part B, h equals 1.2. That's going to give us 1.2 equals 0.6 e to the minus 0.2t plus 0.9. Then we just have to rearrange. We're going to need a logarithm to solve this, but let's start with rearranging. So we'd have 0.6 e to the minus 0.2t would be 0.3, subtracting off the 0.9. Then division by 0.6, that's just a half. So we have e to the minus 0.2t is a half. Then we can rewrite this with a logarithm. So minus 0.2t would be log base e, or natural log of a half. So our final answer for t, not a final answer, sorry. The first value for t would be 1 over minus 0.2 natural log of a half, which, if we run that through the calculator, we have minus 1 over 0.2. Where's the natural log button on this calculator? Shift log of a half. That's 3.465 something. So we know the final answer is going to be 3 hours. And then we need that remaining fraction. So let's take away 3 from this. That's the excess of an hour we've got. So 0.4657 of an hour. So let's just multiply this by 60, and then we'll get the number of minutes on top of the 4 hours. That's 27.9 minutes. How do they want us to round? And it says to the nearest minute. So to the nearest minute, that would be the 28th minute. So 3 hours and 28 minutes. Then for the last part, it says, in the long term, the water level in the tank falls to the same height as the hole. Find, according to the model, the height of the hole from the bottom of the tank. So in the long term, that just means as t gets really large. So if we take our function here again, let's just copy this over to the next page one more time. So we want to understand, what does h tend towards as t tends towards infinity? Oh, sorry. H tends towards what when t tends towards infinity? Well, the only bit that tends towards, that's dependent on t, sorry, is this exponential here, and a negative exponential tends towards 0. So e to the minus 0.2t tends towards 0. So therefore, h is going to tend towards 0.6 times 0 plus 0.9. So h is going to tend to just 9, which would be, and then state the units as well. So that's 9 meters. Sorry, 0.9, excuse me. 0.9 meters. Which is the end of the solution. Moving on to question 8. We've got two functions, f and g. And the first thing says, can we find f of g of 2? Well, first let's start with finding g of 2. So g of 2, which would be plugging x equals 2 into g, obviously. So that would be 5 over 2 times 2 minus 9, which is 5 over 4 minus 9, which is minus 5, which is just minus 1. So then we know that f of g of 2 is the same as just f of minus 1. So just plugging in minus 1 into f, that'd be 4 minus 3 lots of minus 1 squared, which would be just 4 minus 3, which is just 1. Then for part B, that was part A, for part B, we need to find the inverse of g. So let's just write down g quickly. So that would be y equals 5 over 2x minus 9. And then the easy way to find the inverse is if we just swap around x and y and then rearrange back for y. So we start with x equals 5 over 2y minus 9, and then start to rearrange. Let's just flip both sides, I think, would probably be the easiest thing. So if we did that, we would have 1 over x equals 2y minus 9 over 5. Then multiply up by 5. We would get 2y minus 9 equals 5 over x. Then if we need to add the 9 and divide by 2. So that would be y equals be 5 over 2x plus 9 over 2. Then for part C, part 1, it says find g of f of x, giving your answer as a simplified fraction. So we need to just sub in f into g. So f of g of x, that was the right way around, wasn't it? Yes. Oh, sorry, no. G of f of x, excuse me. G of f of x. So wherever we see an x in g, we're just going to replace it with the entirety of f. So that's 5 over 2 lots of f of x, which is just 4 minus 3x squared. So let's put that in a bracket. 4 minus 3, 3x squared, minus 9. Then we'd have 5 over, well, we've got 2 times 4 is 8, minus 9 is minus 1. We'd have minus 1, and then we'd have 2 times minus 3 is minus 6, lots of x squared. I don't like seeing the minus sign on the bottom, so personally I'm going to multiply the top and bottom by minus 1. That would leave us with minus 5 over 1 plus 6x squared is how I'd leave that. Then for part 2, it says deduce the range of g of f of x. So we need to be careful here in that there's a restricted domain applied to g. Which is going to carry on then to, yes, to g of f of x. So if we start with this function, first off, let's see what happens when x equals 0. Whenever I'm finding a range, I like to plot a little graph. So when x is 0, we're going to get minus 5 over 1. So it's going to be minus 5. And then as x gets larger, this denominator is going to grow. So it's going to be minus 5 divided by a larger and larger number, which means it's going to go closer and closer towards the x-axis. And then let's see if there's actually a solution for when y equals 0. At that point, it's minus 5. For when y equals 0, we'd have it's never going to equal 0, is it? Because the denominator is just going to get closer and closer to 0. So if we think about what happens as x tends towards negative infinity, it's also actually just going to get smaller and smaller, isn't it? Because even if x is negative, it's squared. So it's going to tend towards 0 again. So it's going to do something like this. And then we can see actually the lowest point for y is going to be -5. So y is going to be greater than or equal to -5. And then our range is x before. Oh, actually, I misspoke, sorry, actually. So the domain is actually going to come from f because we're doing g of f. So it's all the real numbers are going to go into f, and then all the outputs of that are going to go into g. But we do need to think about the output of 4 minus 3x squared then, don't we? Sorry. So 4 minus 3x squared, if we have a little look at that. So 4 minus 3x squared, that's an x squared, a negative x squared graph that's just been shifted up by 4. So the largest output, like the range of 4 minus 3x squared, is going to just be x is less than or equal to 4. So that's actually not going to affect it too much, is it? Because x equals 4 would be out here somewhere. So it's not good. Like, we're still going to get everything from -5 up towards 0 because we can have all these values over here gives us the things that this section is going to be excluded. So the range would just then be y is greater than or equal to -5. So that is our final answer. Then going back for the last bit, it says the function h is defined by h of x equals this other quadratic where k is a constant. Find the range of values of k for which f of x equals h of x has no real solution, so they don't intersect. So if we want to think about the solutions, let's just actually write the equation out. So if we go back here, this was part, was it part D? Sorry. Yes, part D. F of x equals h of x. The f of x was just our 4 minus 3x squared. And the h of x was the new thing introduced. 2x squared minus 6x plus k. Which is actually, if we simplify it down, is just another quadratic to solve. If we want to find the intersection point, so that would be 5x squared, bring the x squareds over, minus 6x plus k minus 4 equals 0. And if there's no solutions for a quadratic, no roots, that means b squared minus 4ac must be less than 0, the discriminant. So we'd have minus 6 squared minus 4 times 5 times k minus 4 must be less than 0. So 36 minus, let's just do this in steps, 20 lots of k minus 4 is less than 0. 36 minus 20k plus 80 with that double minus there, less than 0. Then 20k would be greater than 36 plus 80 is 116. Then k is greater than 116 over 20. So just checking that, see if it simplifies. 116 over 20 is 29 over 5. So final answer, let's just say k is greater than 29 over 5. So extra correction here, guys, sorry. I should have said for the range earlier that in this section we obviously don't go above 0, do we? So y needs to be greater than -5, but less than 0. So greater than minus 5, less than 0. That's our range, actually. Moving on to question 9. It says the first 3 terms of a geometric sequence are given like so. Use algebra and making your reasoning clear, prove that k equals 5 over 2. Well, if it's a geometric sequence, that means there's a common ratio. So if we divide any term by the previous term, we should get the same thing. In other words, for part A, then, we can use the fact that, well, 9 to the power of 7 minus 2k over 3 to the power of 4k minus 5 must be the same as 3 to the power of 2k minus 1 over 9 to the power of 7 minus 2k. And then this will be a lot easier if everything was 3s and we could simplify the power, which is easy to do because 9 is just 3 squared. So let's just take a minute to simplify 9 to the 7 minus 2k. So 9 to the 7 minus 2k is equal to 3 squared times 7 to the power of 7 minus 2k, which is 3 to the power of 14 minus 4k. So plugging that in now, we'd have 3 to the 14 minus 4k over 3 to the 4k minus 5 equals, I'm just going to expand that bracket out on the last bit, that's 3 to the 2k minus 2 over 3 to the 14 minus 4k. Then we can just apply what we know for indices here. Division means subtraction, and we got to be careful because we're like subtracting and there's double minuses going on. But on the left, we'd have, in fact, let's just write it out. This is what I'd do if I was in my exam to not make a mistake. I would write 14 minus 4k, and where I want to minus something, let's put it in a bracket. 4k minus 5, like that. And on the same on the other side. 3 to the 2k minus 2, minus bracket 14 minus 4k, and now we're not going to miss these double minuses. So we've got 14 minus the minus 5, minus 5, sorry. So that's plus 5, so that's 3 to the 19. And then we've got minus 4k, and then just minus another 4k. So 19 minus 8k, simplified on the left. On the right, we've got 2k and then a double minus 4k. It's 4k, yeah, so plus 4k. So that's 3 to the 6k. Then minus 2 minus 14 is minus 16. And now that we've got it all in base 3 here, the powers must just be the same if this is going to work, right? So 19 minus 8k must equal 6k minus 16, which is just a simple linear equation to solve. So doing that, we would have, let's see, bring the 8k to the right, that would be 14k. And then moving the 16 to the left, that would be 29 plus the 6 is 35. Sorry. 29. Yeah, 35. And oh yeah, sorry, that does work. Yeah. And then sorry. Let's just double check. 35 over 14. That is 5 over 2, sorry. Good. So k is 5 over 2. Excellent. Then for part B, it says, hence find the sum to infinity of the geometric series. So that's a given formula. So S infinity is A, the first term, over 1 minus R, the common ratio. So we need to find A and R. Well, A is just the 3 to the 4k minus 5. That's right, wasn't it? Yeah, 4k minus 5. Oops. So that's 3 to the power of 4 times 5 over 2. minus 5. Let's just plug that in the calculator to make things easy. 3 to the power of 4 times 2.5 is 5 over 2. Oops, what the 4? There we go. And then minus 5. So that's 243 for our first term. And then the r, we can do any of the ratios from before. So let's do 9 to the 7 minus 2k over our 3 to the 4k minus 5, which we've already worked out. It saves us a bit of work. So in brackets, let's have 9 all to the, sorry, as a fraction, 9 to the power of 7 minus 2 times 4.5 again. Sorry, not 4.5, times 5 over 2, 2.5. And then our bottom was just 243, which we knew already. That's a third. So then our final answer is going to be, for S infinity, is 243 over 1 minus a third, or 243 over 2/3. Let's just get the calculator to do that for us again. So 243 over another fraction, 2 over 3, gives us 729 over 2. Does it want it as a decimal? No, it doesn't say, so we'll leave it as a fraction. 729 over 2. Moving on to question 11. Sorry, question 10. We've got the sketch, and it says figure 3 shows the sketch of the curve. The curve crosses the x-axis at point A. Verify that the x-coordinate of A is 4. So verify means we're allowed to just plug in 4 and sorry, verify means that, yeah, sorry, we can plug in 4 and it should come out as y equals 0. So if we plug in 4 for part A, y equals 8 times 4 minus 4 to the power of 5 over 2. Let's just plug that in the calculator to make sure. 8 times 4 minus 4 to the power of 5 over 2, or 2.5, is indeed 0. So that checks out. Then it says use calculus to show that an equation for the line L1 is given by such, sorry, and then L1 is the tangent. So to get the gradient of our tangent, we can differentiate. So let's start with just writing the curve out again. So y was equal to, y was equal to 8x minus x to the 5 over 2. So our derivative, dy by dx, is going to be 8 minus 5 over 2 x to the 3 over 2. And we're interested in the tangent at A, so that's our x-coordinate of 4. So when x equals 4, the gradient of our tangent is going to be 8 minus 5 over 2 times 4 to the 3 over 2. Using our calculator again, 8 minus 2.5, then 4 all to the power of 1.5 is minus 12. And then we know that the point A was actually 4, 0. So if we'd like the equation, let's use y minus 0 equals minus 12 x minus 4. That's going to be y equals minus 12x plus 12 times 4 is 48. So we would get y plus 12x equals 48, which is what they asked for. Then it says line L2 is y equals 8x. Let's mark that on. And then the region R shown in figure 3 is bounded by the curve L1, L2. and by the curve at L1 and L2, good. And then using algebraic integration, can we find the exact value of R? So first off, like R's got a curved side to it, so that's why we need the calculus. But if we think the outer perimeter, we could think of first initially as this. So that's just a triangle, and we know this is the origin, so an x-coordinate of 0. This was 4, 0. So we know the base of our triangle, and then we can find the height of the triangle just by finding that point of intersection. And then if we integrate the curve, so here's our curve, we integrate from 0 to 4, that's going to find all this area here. So we can do the triangle minus our integral, basically. So let's start by finding the height of our triangle and the area of our triangle. So if we go back to this equation, y equals minus 12x plus 48, and we also want to see where it intersects y equals 8x. So we'd have 8x equals minus 12x plus 48. Bring the 12x over, we'd have 20x equals 48. So x is 48 over 20. And I'll just use the calculator to simplify that for me. That's 12 over 5. And then we're going to need the y-coordinate of that. So the y-coordinate is going to be 8 times 12 over 5. So just times our answer in our calculator by 8, which is 96 over 5. So the area of our triangle, I'll erase this from earlier. So the area of our triangle is a half base times height. And the base is just going from 0 to 4, so the base is just 4. Half times 4. And then the height was our y-coordinate of our intersection point that we found, so this height here, which we saw was 96 over 5. Times 96 over 5. And then half times 4 is 2, and then times 96 over 5. So just times this thing in our calculator by 2, which is 192 over 5 for the area of our triangle. Then for the curved area, we're going to need to do the integral. So that's the integral of our function 8x minus x to the 5 over 2. And we're going to integrate between 0 and 4, wasn't it? Yeah. Sorry, let's just check again. Yeah, 0 to 4. Good. So integrating this, 8x to the 1, raise the power goes to 2, and divide by that gives us 4x squared. And then on the x to the 5 over 2, raise the power once more, that's 7 over 2. Divide by 7 over 2, that's the same as multiplying by 2 over 7. So minus 2 over 7, x to the 7 over 2, evaluated from between 4 and 0. Well, the bottom limit is just going to give us 0, because everything's got a factor of x on it, and x is going to be 0 for the bottom limit, so we just need to worry about the top limit. That's 4 lots of 4 squared minus 2/7 of 4 to the 7 over 2. Let's plug that in our calculator. So 4 lots of 4 squared minus 2 over 7 times 4 to the 7 over 2. 7 over 2 is 3.5. That gives us 192 over 7. So then our shaded region R is 192 over 5 from our triangle before, minus 192 over 7 for our integral we just calculated. So we'll do 192 over 5 think I said 4 earlier. I meant to say 5. Minus the answer we just got, which gives us 384 over 35. Okay, moving on now to question 11. It says figure 4 shows the design of a badge. ABCOA is a semicircle with center O and diameter 10, so let's just mark on that. That's diameter 10. OB is the arc of a circle with center A and radius 5. So that means there's another sector of a circle embedded like here. So before I get ahead of myself, I think I'm just going to put in that one side from A to B. So if I put that in from A to B, then we know that this is 5 centimeters and this is 5 centimeters because it's the half of the diameter from A to O. And if we think about it as well, if the full thing is a semicircle, then if I draw in O to B, that's 5 centimeters also. So that's going to be useful because that's an equilateral triangle. And that's a really good thing in these kind of questions. Like, don't worry about the full question. Try and see what things you can just quickly work out, and then they'll probably be useful later. But yeah, so we've got that. Yeah, it just says find the shaded area R. So the shaded area R is going to be the full semicircle minus this white bit here, which we can think of as just the triangle plus these two sort of petals, I'll call them here, or segments, probably the better word. Yeah, let's just start with the triangle then. So if I draw a little sketch of the triangle for us. Oops. So we've got a triangle, each side is 5, and if it's an equilateral triangle, then the total internal angle is pi, and each angle must be the same, so this must be pi divided by 3. So we can find the area of this really easily with just a half AB sine C. So that's a half times 5 times 5 times sine of pi on 3. If we plug that in the calculator quickly, so 0.5 times 5 times 5 times sine of pi on 3. Oops. Just check we're in radians. Yes, we are. Sine pi over 3. That's 25 root 3 over 4. Oops. 25 over 4 root 3, same thing. Then we need to work out our segment. So if I draw the full sector quickly, if this is our sector, let's draw it a bit better than that actually. So there's our sector, and remember, we cut this down here. This triangle I formed here is just the same triangle I had a minute ago. So our segment area then is going to be the full sector of a circle, which is a half r squared theta if we're working in radians, and then take away the triangle. So take away the 25 over 4 root 3. So that's going to be a half times 5 squared times pi on 3 minus 25 over 4 root 3. Simplifying that up, we're going to have 25 over 6 pi. Minus the 25 over 4 root 3 still. Oops, 25. So then, yeah, we've got to put the pieces together now. So the shaded area R is going to be the full semicircle minus 2 lots of, let's just call that semicircle properly. Semicircle minus 2 lots of the segments minus the triangle ones. So bringing that all together, a semicircle is just going to be half r squared theta, sorry, half of pi r squared, sorry. So a half times pi times the radius is 5, so times 5 squared, minus 2 lots of our segment, which was this guy down here. I'm just going to copy and paste him. So we need 2 lots of that guy. And then minus the triangle, which was just the 25 over 4 root 3. So that's going to be 25 over 2 pi. Then we've got minus 50 over 6 pi. And then we've got a double minus, so plus 25 over 2 root 3. And then another minus 25 over 4 root 3. So grouping these things up, we've got 25 over 2 minus 50 over 6. 25 over 2 minus 50 over 6. That's 25 over 6 lots of pi. Then we've got 25 over 2 minus 20 over 5 over 4 is just another 25 over 4. So plus 25 over 4 root 3, which is our final answer. Moving on to question 12. It says, express 140 cos theta minus 480 sine theta in the form k cos theta plus alpha. So that's one of those harmonic form type things you've been taught. So let's first expand out k cos theta plus alpha using the addition formulae. So, well, I'll just write out the addition formulae so you know what I'm referencing. So cos A plus or minus B is the same as cos of A cos of B, and the cos it changes sign, so minus plus sine of A sine of B. So then if we apply that, then we're going to say, well, 140 cos theta minus 480 sine theta, is equal to, and now we'll apply our addition formula to this form. So it's going to be cos theta cos alpha, but times k. So k, and I'll just reorder that actually. So I'll write it as k cos alpha cos theta. And then we've got a plus here, so we're taking a minus in our formula. Minus, and it's going to be k sine alpha sine theta, again just reordering. Because now what we can do is we can compare the coefficients. So if these two guys are equal, we must have the same amount of cos theta. So 140 must equal k cos alpha. So let's write that down. So k cos alpha must equal 140. And then if we do the same thing, but for the other coefficient, so we've got minus 480 sine theta is minus k sine alpha sine theta. So the minus 480 must be the same as, well, we just omit the minus sign as it's there on both. 480 must be the same as k sine alpha. So k sine alpha equals 480. And then the quick way to get k is, this is actually just a triangle if you think about it. This is a right angle triangle where this is k and this is alpha. So this would be 140 for k cos alpha resolving in k sine alpha would be this side. So k is just some Pythagoras. So k is the square root of 140 squared plus 480 squared. Yep, so let's put that in the calculator. 140 squared plus 480 squared. That's 500. Then the nice way to get alpha is we can divide these two equations. So if I divide the equations, we'd have k sine alpha over k cos alpha would be 480 divided by 140. If we simplify that, 480 over 140, that's 24/7. And on the left, the k's are going to cancel, leaving us sine alpha over cos alpha, which we should recognize as just a tan alpha. So we have tan alpha is 24/7. And let's just check. So they want alpha in degrees, so let's swap over to degrees. Angle unit, degrees. And then we do inverse tan of 24/7. That's that number there. What do we want to round to? So 2 decimal places. That would give us 73.74 to 2 decimal places. Sorry. Yeah, 73.74. Yeah, that's correct. 0.74 degrees to 2 dp. Excellent. So moving on, it now says a scientist studies the number of rabbits and the number of foxes in a wood for 1 year. The number of rabbits R is modeled by this equation. So in these questions, they always follow on with the bit we just did. So if we try and draw some similarities, this bit is just this bit, except theta is now 30t. So we can use our working from part A, but just replace it with 30t. And it says, find a complete equation for the model. Well, let's first just write out in that form, now that we've deduced that. So the number of rabbits is going to be, what do they call it? A plus k was 500. And then it was, what was the form? We used cos. So cos, but the theta is now 30t. Yep. 30t. And then plus the 73.74 for our alpha. Okay, so that's the real form of the model we're going to use. And it says t is the months, where t months is the time after the start of the year, and a is a constant. It says, given that during the year, the maximum number of rabbits in the wood is 1,500, complete this equation. So we need to find a. So they're saying R max is 1,500. Well, if we think about it, the maximum value of this is just the 500, because a cos graph goes between 1 and -1. Then if we multiply by 500, it would go between 500 and -500. So the maximum of that is 500. So therefore, A must be the 1,000 to finish that off. So our models now R is 1,000 plus 500 cos 30t plus 73.74 degrees. And then for part 2, it says, hence write down the minimum number of rabbits in the wood during the year. So write down means we can just deduce it, but we're just going to use the same logic we had a moment ago. So if we want the minimum, we want to make this guy negative. And the biggest negative we can make it would be -500. So R min then, the minimum number of rabbits would be 1,000 minus 500, which would be 500 rabbits. Then moving on to part C, it says the actual number of rabbits in the wood is at its minimum value in the middle of April. Use this information to comment on the model for the number of rabbits. So we're going to have to see when our minimum number of rabbits is predicted by the model and compare that to this info they've just given us. So our minimum number occurred when the cos bit, so cos 30t plus 73.74, that needs to be equal to -1 in order for us to, the 500 times the -1 would have given us the -500 that we wanted before. So we need to solve that equation and see what it tells us for t. So let's just write that on the next page, actually. So cos 30t plus 73.74 equals -1. So let's start with just thinking, well, 30t plus 73.74 then. That would occur on the cos graph at 180 degrees. So 180 degrees. But the cos graph repeats every 360 degrees. So if we might need more solutions, we could add plus or minus 360 to this. That would encapsulate all the solutions. Then let's take 73.74 away. So we'd have 30t would be 106.26 degrees, plus or minus 360 still. And then dividing by the 30, we'd have t is this 106.26 over 30, plus or minus 360 over 30, that's 12, I'll just check. Yeah, 12, plus or minus 12 degrees. Okay, so let's actually check the units of time again. So time, where t is in months. So, oops. Let's just calculate this first solution where we can, sorry, I should have had a k here before, sorry, just so we can add as many amounts of k as we like, of 360 as we like. But let's just think about the first solution where we don't add 360 at all. So that would just be the 106 over, sorry, 106.26 over the 30. Format that as a decimal. Okay, so 3.542. And then we can actually see now that I've corrected this and we're thinking about it properly. So the 12 is going to take us obviously into the next or the previous year, which we're not interested in. So 3.542, and t is measured from the start of the year, wasn't it? After the start of the year. So yeah, t equals 0 is the beginning of January. So after t equals 1, we're in February. T equals 2, we're in March. After t equals 3, we're in April. Sorry, did I say that right? Let me try that again. At t equals 0, we're in January, excuse me. Call it Jan. At the end of t equals, well, actually, let's say t equals 1 through to t equals 2. That's all February. T equals 2 to 3. That would be March. So then t equals 3 to 4 would be April. So it looks like our model's in agreement. What did they say? The actual number of rabbits in the wood is at its minimum value in the middle of April. And it is actually halfway through So 3.5 is the middle of April. So therefore, we'd say the model does predict it well. What did they actually ask? Sorry. Comment on the model for the number of rabbits. Yeah, so therefore the model predicts R well. Okay. Then the last bit, it says the number of foxes F in the wood during the same year is modeled by another equation. The number of foxes is at its minimum after T months. Find, according to the models, the number of rabbits in the wood at time T months. Okay, so we need to first find this value of T, where the foxes are at a minimum, and then plug that back into R to find the rabbits at that time. So this guy is at a minimum. If we apply the same logic, it's when this bit here would be -1, because we'd have 100 plus 70 times -1, which would give us the 30, which is as small as it could ever go. So that's sine 30t plus 70 equals -1 is what we need to solve. Let's call it capital T, because that's what it actually said it was. It equals -1. If we think about that on the sine graph, that happens when the angle goes to 270 degrees. And just in case we need the solutions again, I'm going to say plus or minus k amounts of 360 degrees. So taking off the 70 first, we'd have 30t equals 200 degrees plus or minus plus or minus the k360 still. And then divide by 30, and we get t is 200 over 30, that's the same as 20 over 3 degrees, plus or minus the k lots of 12 degrees again. So we're not going to need the k lots of 12 degrees. So just taking that value of 20 over 3 and plugging it into R, so R equals, what was our model? It was, what was A? 1,000. So R is 1,000 plus our 500. Let's just copy and paste this, sorry. Don't keep forgetting it. Just paste it here. So plus the 500. Where have we gone? There we go. Plus the 500 cos of 30 times 20 over 3 plus 75. Is that 75 or 73? 73 plus the 73.74. So what does that come out as if we plug it in the calculator? We've got 1,000 plus 500 cos of 30 times 20 over 3 plus 73.74. Close that. 1,032.6 rabbits, does it say to round? It doesn't say to round, but we can't have 0.6 for a rabbit, so let's just say we'll round to the nearest rabbit. So 1,033 rabbits. Okay, moving on to question 13. It says, given that a is a positive constant, use the substitution x equals a sine squared theta to convert this integral into the right-hand side integral. So let's just start with the process of substitution. So there's 3 steps we're going to have to do. We're going to have to change the limits, the function itself, or the integrand, and the differential. Let's do the limits first. That's easy. So if we have a top limit of a, then a would equal a sine squared theta. So then sine squared theta would equal 1. So sine theta would be plus or minus 1. And one of those solutions is pi on 2. So we'll just take the pi on 2, as that's what it says. Then repeating the process, we'd have 0 equals a sine squared theta. So we get sine squared theta equals 0, which is going to just lead to theta equals 0 once we go through the same process. So we've confirmed the limits, check out. Let's see, I think I'll do the differential next, because like normally with these trig things, some kind of simplification with trig identities goes on, so I'll do that first, I think. So first, if we find dx by d theta, we have to be a bit careful here because we've got 2 functions going on. We've got this, we've got the sine function, but it's all squared. So if you struggle with that, a little tip is I used to do this. I used to write it in a bracket so I could recognize like the layers of the function, if that makes sense. And then applying the chain rule, which is what we need, we do the inside function first. Well, you still have that a, obviously, but the inside function sine goes to cos theta. Then just differentiating the power, a squared would go down to just 2 times the thing we had, all to the power of 1. So just going to have a 2 sine theta left. So that's 2a sine theta cos theta, which looks promising because that's already if we think about sine 2 theta is 2 sine theta cos theta, which is in sine 2 theta is in our answer. So I think I'll go ahead and just include that. So that's just a times sine 2 theta. Then we just have to sub in for our function now. So our integral we now know is from 0 to pi on 2. And it's x to the half, so it's the square root of all this, of our substitution. So that's root a, that's root a times the square root of the sine squared, that's just the sine theta. And then we've got the square root of a minus x, which is just the a sine squared theta left alone. And then we've got to replace our dx with a d theta. So we knew here that like dx d theta was a sine theta, so dx must just be a times sine 2 theta d theta. So we'll plug that in at the end as well. So times a sine 2 theta d theta. And then we need to start simplifying this down. Straight away, there's 2 factors of a here. So I'll pull a root a out of the whole thing, which would nicely convert that into an a. And then we've also got this a here, but perhaps I'll do that in another line, so we're not doing too much. So pi over 2, then we'd have a sine theta. And if I pulled that a out, inside we'd have left 1 minus sine squared theta times another a sine 2 theta d theta. Let's copy and paste this to the next page. So 1 minus sine squared theta, we should recognize that as cos squared theta. And then square rooting all that, that would just be just a cos theta on its own. So fully simplifying, we'd have a sine theta cos theta times another a sine 2 theta d theta between 0 and pi over 2 still. And the a's are going to combine to give us just an a squared. But sine theta cos theta, that's the same thing we did a moment ago, just missing the 2, but we can correct for that just by putting in a half. So that's a half of sine 2 theta times another sine 2 theta, and then we're there. Just got to pull the half and the a squared out. So that is a half a squared of the integral times the integral 0 to pi over 2 of sine squared of 2 theta, d theta. So that's part A. Then it says, hence use algebraic integration to show that, that integral we started with is some constant times pi a squared, where k is a constant to be found. So we just have to do this integral now. So the integral of sine squared is a standard integral we should know. We can utilize the cos double angle formula, but we're actually starting with 2 theta. So we're going to need the 4 theta double angle formula, in fact. So cos 4 theta, using our double angle formulas, is, which way around is it, sorry? It's 1 minus 2 sine squared 2 theta. So if we rearrange for sine squared 2 theta, that's going to be a half of 1 minus cos 4 theta. So we can do the integral of that instead of the sine squared. So then our answer, our integral, is a half a squared times the integral from 0 to pi on 2 of a half 1 minus cos 4 theta d theta. Let's pull this to the next page again. So then we'll pull out the half. That would be a quarter a squared. And we'd have the 1 minus cos 4 theta left between 0 and pi on 2 still, d theta. So let's just leave the quarter a squared alone for the minute, have this all in a big bracket. So integrating, let's have a square bracket actually, indicate we'd put some limits in. So 1 integrated is just going to give us a theta. Then if we integrate cos 4 theta, it's going to be a sine 4 theta. If we think about it, differentiating that would give us a 4, which wasn't there originally, so we need to put a quarter in to correct for that. And then we need to plug in our limits of 0 and pi on 2. So just writing this all out with a quarter a squared, and now I'll do big bracket. Upper limit is pi on 2 minus a quarter sine 4 times pi on 2. That would just be sine of 2 pi. And then plugging in the lower limit, that would be 0 minus a quarter sine of 0. So that second bracket's really nice because sine of 0 is 0. So 0 minus 0 is all 0. So we can just forget about that entirely. Well, let's just equal 0, we'll say. And then this guy, sine of 2 pi is actually also equal to 0. So this little bit here is all 0. So we're just left with this pi on 2. So our final answer would be a quarter a squared times pi on 2, which is an 1/8 a squared times pi. Let's just check that's in the right form. Yeah, so k pi a squared. So our k is just 1/8, an 1/8. Moving on to question 14. it says a balloon is being inflated. In a simple model, the balloon is modeled as a sphere. The rate of increase of the radius of the balloon is inversely proportional to the square root of the radius of the balloon. Let's just write that down. This is going to be used for part A most likely. The rate of increase of the radius, so that's dr by dt. And then he says inversely proportional, so proportional to 1 over the square root of r. And it says write down a differential equation. Okay, so make that a differential equation, we just have to turn it into an equality. So if we want to turn a proportionality into an equality, we just have to put it as a multiplying constant, so k over root r. Then it says at the instant when t equals 10, the radius is 16. So r equals 16 is right. Yeah, r is measured in centimeters. Good, and the radius is increasing at a rate of 0.9. So they're saying also that dr by dt is equal to 0.9 at that time. Okay, so let's start by just solving this differential equation. So first thing I'm going to do is actually write it, because I'm going to integrate. Let's write it as a power of r. So that would be the same as k times r to the minus half. Is that right? Sorry. Increase the radius inverse proportional to the square root. Yeah. Okay. So continuing on from there, let's just write the differential equation again out over here. dr by dt equal to k r to the minus half. So to integrate, so to solve this, we need to think of it as a differential equation. So we'll bring the r to the half to the left-hand side. If I multiply both sides by r to the half, that would leave us with this, r to the half dr, and then move the dt to the other side. That would be equal to kt. Sorry, k times dt. Then we need to integrate both sides to solve. So integrating this on the left, we raise the power by 1, that would be 3 over 2, then divide by the new power. So dividing by 3 over 2 is the same as multiplying by 2/3. That would be equal to kt plus a constant. And then we need to check, okay, well, let's use our information to be able to find k and c. So they told us when t equals 10, the radius is 16. So t equals 10, r equals 16. And they also said that dr by dt was 0.9. So actually, let's use the dr by dt information first, because we can see, yeah, like that we can find k immediately using that equation here. So we'd have dr by dt, so 0.9 must equal k times 16 to the power of minus a half. Oops, minus a half. So 16 to minus a half, that's 1 over the square root of 16, or 1 over 4. So k would be 0.9 times 4 then, which is 3.6. And then now we have k, we can plug that in to find r plus c with the other information. So we got 2/3 of r, which is 16 again, to the 3 over 2 equals 3.6 times t, which is 10, plus c. So to find c, let's just plug that in the calculator. So that would be 2 over 3 times 16 to the power of 3 over 2, that's 1.5, and then we have to subtract that other term, so 3.6 times 10, so minus 36. is 20 over 3. And do they want it rounded at all? They want it as not as in a fractional form. So let's actually write that. So 20 over 3, format that. Oh, that's not very nice. Actually, we'll leave it as 20 over 3 for now. And then we'll fix it when we rearrange for the end, because we just want to rearrange this. So 2/3 of r to the 3 over 2 is 3.6 t plus 20 over 3. So we need to multiply by 3 and then divide by 2. So 3.6 divided by 2, but multiplied by 3. That's 27 over 5. Let's just check that as the 5.2 they want, 7.4 they wanted. It is. So r to the 3 over 2 is 5.4t. And then 20 over 3 times 3, that just makes it 20. And then divided by 2, that makes it 10. So that is what they asked for. Then it says, hence find the radius of the balloon when t equals 20. So that's just solving, that's just plugging in t equals 20 and solving for r. So if we go back to this, what we're going to do is we're going to need to square all that and then cube root it. So r would be the cube root of 5.4t plus 10 all squared. Just thinking that the squaring gets rid of this, we're raising both sides to the power of 2, then raising both sides to the power of a third gets rid of that, and then you've got r to the 1, which is what you want. And then we're interested in this for t equals 20. So at t equals 20, we get r equal to, plugging that in, so the cube root of 5.4 times 20 plus 10 all squared. That gives us 24. 24.05 ... We need to round that. The nearest millimeter. Well, what's r measured in? R is measured in centimeters. So if we want that in centimeters, millimeters, it's 24.05 millimeters. We're gonna have to multiply it by 10, and then, so let's take this number on our calculator, multiply it by 10, and then rounding to the nearest millimeter, we're going to be rounding up to 241 millimeters. That's in centimeters, which is same as 241 millimeters rounded up. Then it says, hence suggest a limitation of this model. Sorry, not hence. It just says suggest a limitation of this model. So what are we modeling here? The balloon is, we're just doing the radius of a balloon in time. Well, this function's only ever going to grow. So it's predicting the balloon's just going to grow forever, which doesn't sound very realistic. So I would assume the balloon would pop at some point if you inflated it too far. So if we want to sort of phrase that a bit better, we'd say, okay, well, as t tends towards infinity, r tends towards infinity, which is not a good model for large values of t. As at some point the balloon should pop. Okay, moving on to the last question now. Part 1 says, show that k squared minus 4k plus 5 is positive for all real values of k. That's kind of like a standard proof, just showing a quadratic's always positive. So the trick is to just complete the square. So you complete the square, we'd have k minus 2 all squared. We have to take away a 4 and then add the 5 back on, so that's plus 1. And then to finish the proof, we know, well, k minus 2 squared is always greater than or equal to 0, as it's a squared number. You can't square any real number and get something negative. So therefore, if you take any number greater than or equal to 0 and you add 1, it's going to have to be strictly bigger than 0. So that finishes part 1. Okay, now moving on to part 2. It says a student was asked to prove by contradiction there are no positive integers x and y such that 3x plus 2y times 2x minus 5y equals 28. And then we've got the start of his proof. He says, assume that the positive integers x and y exist such that they multiply in this fashion to give 28. And then he started by looking at one of the possible ways this could happen, which would be 14 times 2. So the 3x plus 2y is the 14, and the 2x minus 5y is 2. And he's shown that that gives a contradiction, that x and y in that case are not integers. But what he's failed to do is consider all the possible options. So to complete the proof, we need to actually think about all the possible combinations of the pairs of factors of 28. So if we start thinking like that, well, 28 could be plus or minus 28 times plus or minus 1. It could be plus or minus 14 times plus or minus 2. And it could also be plus or minus 7 times plus or minus 4. And bearing in mind, we've also got to prove like each, like 28 and 1 as well as 1 and 28. So we can assign each number to each bracket individually, like each number to both brackets. So there's double these amount of pairs. That would be a lot of options. So let's see if we can eliminate some of them a bit more easily. Well, the fact that the x and y are positive integers means that we could never have them add up, like in this case, to give something negative. So you could never plug any of the negative examples in for this. Which means the other guy would have to be positive as well, because if that guy's positive, this guy's going to be positive for it to be possible still. So that means all the negative ones are just out. So then we just have to worry about 28 times 1 as well as 1 times 28. We have to do 14 times 2 as well as 2 times 14. We have to do 7 times 4 as well as 4 times 7. Except he's already done one of them for us. He's done 14 times 2 for us already. So we've got 5 bits of grunt work to do. We've got to prove these 5 other cases, unfortunately. But let's start. So we'd have 3x plus 2y. Let's do the 28. Let's do this. Let's label them. That's case 1, case 2, case 3, case 4, and case 5. So we're doing case 1 at the moment. That's 3x plus 2y is 28. And then the other equation we'd get from this would be 2x minus 5y equals 1. How should we rearrange this? We can get... No, let's multiply one of them. Let's multiply... do I want to multiply? No, let's rearrange. I've changed my mind. So if I divide everything by 2 here, we'd have y equals 14 minus 3 over 2x. Subbing that in here, we'd have 2x minus 5 times 14 minus 3 over 2x equals equals 1. Solving that would give us 2x minus, plus 15 over 2. What's 2 plus 15 over 2? That's 19 over 2. So that'll be 19 over 2x. Then we've got minus 5 times 14, but that's going to be added to the other side to plus 1. So 5 times 14. And then plus the 1. 71. Well, that's x there, and then 71. Times that by 2. And divide by 19. That automatically doesn't give us a solution, an x integer. So we don't have to worry about it for the y. We can just stop there. So non-integer. So case 1 doesn't work. We're going to have to follow this through for all the cases now. So let's do case 2, which is 1 in 28. So that is 3x plus 2y equals 1. And the other one is 2x minus 5y equals 28. So for this one, I think I will rearrange this for x. So we can divide it all by 2 and add the y part over. So x would be 14 minus 5 over 2y. Sub that into the left-hand one. So we'd have 3 lots of 14 minus 5 over 2y plus 2y equals 1, which is going to give us 3 times 14, 42. Bring the 1 over this side. That would be 41. And then we've got 3 times minus 5 over 2, 2.5. And then plus 2. That's minus 11 over 2y. Equals 0 then. We solve that for y. Y would be 41 times the 2 divided by 11, which is 82 over 11. So that's also a non-integer, so we can stop there. Then case 3. Case 3 was 2 and 14. So we'll have 3x plus 2y equals 2. 2x minus 5y equals 14. Solving this one, I'm going to choose to rearrange this equation for y. So y would equal 1 minus 3 over 2x. Plugging that in the other side, we would get 2x minus 5 times 1 minus 3 over 2x equals 14. Bringing that all together, we'd have 2, and it's a double minus on that x, so plus 5 times 1.5. That's 19 over 2x. Then we've got just a minus 5. Bring that over the other side. So that would be added to make it 19 on the other side. So that case is a bit annoying because that actually does give us an integer for x. That gives us x equals 2. But if we check for y, y would be 1 minus... Oh shoot, what have I done wrong? Made a mistake, sorry guys, let me have a little look. So we were doing case 2, which was 2 and 14. I've written the equation, is that right? Yeah, 2x plus 2y equals 2, 2x minus 5y equals 14. Oh, there it is. That's a 2, not a 1. Sorry about that. That's a 2. That's a 2, which changes this to 14 plus a 10, which is 24. Let's get rid of this because this is wrong. So 24. So then we get 48 over 19, which is a non-integer. So that solves that case. 2 more cases to go. Case 4. That was going to be 7 and 4. So we'd have 3x plus 2y equals 7. And 2x minus 5y equals 4. Solving this, how would I go about that? I think I'll rearrange this guy for x. So we'd have 2 minus 5x is 2 minus 5 over 2y. Plug that in this guy. That would be 3 times 2 minus 5 over 2y plus 2y equals 7. Bringing that all together, we've got 6 minus, will be 3 times minus 2.5. But then we've got to add the 2 on. That's minus 11 over 2y equals 7. So 11 over 2y would equal minus 1. So y would be minus 2 over 11. That's a non-integer. So that's that case solved as well. Case 5, last one. Case 5 would just be the same thing but the other way around. So 3x plus 2y equals 4. 2x minus 5y equals 7. Solving one last time, let's rearrange this guy for y. That would be y equals 2 minus 3 over 2x. Yeah. Then plugging that into this guy, we would have 2x minus 5 times 2 minus 3 over 2x equals 7. We've got 2 plus, and it's double minus, so a plus 15 over 2. 15 over 2. That's 19 over 2x. Then we've got minus 5 times 2, that's a 10. Let's take that over the other side, which will make it a minus 3 on the other side, the 7 minus 10. And then solving for x one last time, that gives us minus 6 over 19, which again is a non-integer. So that means like all possible cases. Oh, let's try and write it legibly. All possible cases leads to a contradiction. Therefore, no integer solutions for xy to, what was the equation? 3x plus 2y times 2x minus 5y equals 28. That's the end of the video, guys. I hope you found it helpful. If you did, please drop it a like, that helps me out a lot, and consider subscribing to the channel to find out when I release new videos. Thanks, and I'll see you in the next one.